let's look at u substitution. Now, integration is basically anti-differentiation, especially for indefinite integrals. So if we had the integral of something like x dx, we'd simply use the reverse processes of differentiation, like the power rule. So this becomes x squared over 2, and as we can see, if we take the derivative of this, the 2 comes down, and this simply becomes, once again, x. So all we're doing is reversing that process to get x squared over 2. U substitution is another important method of anti-differentiation, coming itself from the most important method of differentiation, which is chain rule. Let's write out once again what chain rule is. It says that if I have a function f of g of x, its derivative is equal to f prime of g of x times g prime of x. So if I had an integral that was easily noticeable in this form, you could immediately integrate it into f of g of x. But most times it's not going to be that simple, so we instead use u substitution, where we say this is u, and we rearrange the integral to get it into a form that looks like f of u du, which then is typically much simpler than this long complicated expression. Now let's look at this integral. So we have 3x times square root of 1 plus x squared dx. And we can't distribute anything here because this is all under a square root. So we don't have an elementary way of anti-differentiating this. Let's use a u substitution, and let's set u equal to this expression here, 1 plus x squared. So I'm going to say u is equal to 1 plus x squared. Now when we rewrite the integral, it's going to become the integral of 3x square root. Now instead of 1 plus x squared, that's all going to be replaced by u dx. However, this brings up the point of this dx in the integral. See, this is the variable that we are integrating with respect to, meaning we can only apply our processes such as our reverse power rule and anything else we might use if the variable is x. Because u is not x, we cannot apply these processes just yet. So somehow we have to transform this integral into the form of the integral of something done to u du. It's very important that this is du, otherwise we cannot integrate it. And so how do we do that? Well, we go back to where we initially set the values for u. And we say, okay, if this is u, we're going to take du over dx is going to be equal to 2x, right? And now we're going to rearrange it this way. We're going to say that du is equal to 2x dx. Now, here's an important thing to note. Although it might look like we treated this like a fraction and we simply multiplied this to that side, remember, this differential notation is not a fraction, but it was designed historically to intuitively behave like one. And so this equality holds true even though these aren't fractions. One small note is that another way to think about this is simply in terms of what du and dx actually are. They're differentials, or essentially dx is an infinitesimal amount of x. So for every small change we have in x, du is going to change by 2x times that amount. So although it might not be an incredibly intuitive understanding of it, it's very easy to treat it like a fraction and say because du over dx is equal to 2x, we can therefore say du is equal to 2x dx, and this is a technique that will work whenever we need to do u substitution in our integrals. So we can say that du is equal to 2x dx. Here we have 3x times dx, not 2x, but this can easily be rearranged to suit the form we want. So I can say this is equal to 2x, and then to make sure that I'm not changing the actual value of the expression, I'm going to multiply it by 3 over 2 square root u dx. Now, because we actually have this 2x dx term, we can replace this with du, and therefore this becomes the integral of 3 over 2 square root u du. And this is a much easier function to integrate because we can just use our power rule. Remember, square root of u is simply equal to u to the 1/2. So I'm going to take the coefficient outside, and it's going to become 3 over 2 integral of u to the 1/2 du, which is going to become 3 over 2 times, I'm going to use my reverse power rule, u to the 3 over 2 divided by 3 times 2. This 3 over 2 is going to cancel out with this 2/3, leaving me with u to the 3 over 2 plus c. However, I'm not done yet, because I started the integral in terms of x, and now I've solved it in terms of u. I still need to go back and replace every instance with u in terms of x. So what I have is u to the 3 over 2 plus c. I'm going to replace this with 1 plus x squared to the 3 over 2 plus c. And we can check our answer. If I take the derivative of this, firstly, the c goes away, it becomes 0. Secondly, this becomes 3 over 2, 1 plus x squared to the 1/2, which is a square root, times 2x. The 2 and 2 cancel out, and what we're left with is 3x square root of 1 plus x squared. And so we verified that this is the correct integral of this, doing it via a u substitution. Let's look at another problem. Let's look at the integral of dx divided by x ln x. Now, our dx is here, but again, we don't have any elementary ways of anti-differentiating 1 over x ln x. So let's use a u sub. Let's note that the derivative of ln x, so d over dx ln x, is equal to 1 over x. And what we have here is 1 over x. And what we have multiplied by it is a function in terms of ln x. So I'm going to rewrite this just to make it a lot more apparent. This is equal to 1 over x times 1 over ln x, the integral with respect to x. That's why we have dx here. This looks exactly like something that we would use our reverse chain rule or our u sub with. So we're going to say u is equal to ln x, and we're going to say that du over dx is equal to 1 over x, and therefore du is equal to 1 over x dx. That's exactly what we have here. So we can replace both of these terms with du. We can replace this term with 1 over u. And therefore our integral becomes the integral of 1 over u du. This is a very easy elementary integral. This is simply ln u plus c. Remember, our u is actually equal to ln x. So as our last step, we're going to take this integral that we have in terms of u, this solved integral, and simply plug x back in. So this becomes ln of ln x plus c. And this is our final integral. Let's look at another problem. This is the integral of tan x dx. Now, unlike sine and cosine, tangent x does not have a very elementary integral. So let's look at what we can do. First, let's rewrite the integral. Sine x over cosine x dx. Now, remember, the derivative of cosine is negative sine. So what we have here is a u sub, where we can say u is equal to cosine x, and therefore du over dx is equal to negative sine x. So du is equal to negative sine x dx. So I'm going to once again rewrite this integral. I'm going to make it negative sine x over cosine x dx. And now our negative sine x dx is going to become du, and our cosine x is going to become u. So this integral has now transformed into negative integral of du over u, where our u is equal to cosine x. This becomes negative ln u. Once again, all we have to do is plug in cosine x wherever we have u, and therefore this becomes negative ln cosine x plus c, which is also equivalent to ln secant x plus c, and therefore this is the integral of tangent x. Let's look at one more trigonometric integral, where it's the integral of sine squared x cosine cubed x dx. Now, as we saw in the last integral, if we have a function in terms of either sine or cosine, and we have it multiplied by the other function, so either cosine or sine, then we can treat one of them as u, and the other one times dx will become some form of du, either du or negative du, depending on which one we choose. Let's see how we can apply that to this function. Because this one is squared and this one is cubed, we can't immediately spot any u and du. So what I'm going to do is I'm going to rewrite this so we get something that's in terms of sine times cosine to the 1, because that makes it incredibly easy to make this u and this du. Let's rewrite this as sine squared x cos squared x cos x dx. And remember, if you see your trigonometric identity here, cosine x can be rewritten in terms of sine. It's 1 minus sine squared x. And therefore, let's rewrite it that way, and then our u sub becomes apparent. This is sine squared x times 1 minus sine squared x cosine x dx. Let's do a u sub. We're going to put our u is equal to sine x, and therefore our du is equal to cos x dx. I immediately skipped moving dx over to this side. This holds true. Here is our du, and all of this we can write in terms of u. Our integral now becomes u squared 1 minus u squared du. Now this we can simply distribute and then use our power rule. So this is going to become the integral of u squared minus u to the 4th du, which then with our power rule becomes u cubed over 3 minus u to the 5th over 5 plus c. As our last step, wherever we see u, we have to now write it in terms of x, because that's what our original problem asked for. We're going to take this integral and replace u with sine x. It becomes sine cubed x over 3 minus sine to the 5th x divided by 5 plus c. And so this is our final answer. Here, let's try this one quickly. So although this might look complicated, it soon becomes very apparent. Let's treat this, because it's the higher degree expression, as u. So this full thing is going to be u. So if u is equal to sine 3x minus x cubed, our du is going to be equal to 3 cos 3x minus 3x squared dx. And now what we have here is very similar. It's not exactly the same, but this is essentially du divided by 3 because it doesn't have that extra 3 factor in it. We're going to rewrite this in terms of u. So I'm going to write first u, and then what we have here is actually du over 3, and that's our integral, u to the 4th, because there's a 4 here. So it's u to the 4th du over 3. I'm going to take the 1/3 outside. It becomes 1/3 integral of u to the 4th du, and this is an incredibly elementary integral. It becomes 1/3 times u to the 5th over 5. So therefore, u to the 5 over 15. As our last step, even though our u is really big, it doesn't change. I simply have to plug in whatever we set u as wherever I see it. So it becomes sine 3x minus x cubed to the 5th divided by 15 plus c. And this is our antiderivative. Here is a slightly different type of problem. Let's suppose my integral is x cubed times square root of 1 minus 2x squared, all with respect to x. Now, similar to the first problem we did, I'm going to set the exact same thing as u. I'm going to say this is equal to u. U is equal to 1 minus 2x squared, and therefore du is equal to negative 4x dx. What we have here is not quite that, so let's rewrite the integral in terms of u and x just so we can see what we have. I'm going to say negative 4x divided by negative 4, so the value doesn't change, times x squared, so keep in mind this entire expression is still equal to x cubed, times square root of u dx. If we look at this negative 4x dx, this is actually equal to du. We can rewrite our integral in almost terms of u. We can say du over negative 4 x squared root u. We have our du here, so now it's in terms of u, but we still have this x term here. So how do we get rid of this? Well, let's go back to what we originally set u as, and let's rearrange the equation. Let's say u minus 1 is equal to negative 2x squared, therefore 1 minus u over 2 is equal to x squared. So now we know what x squared is in terms of u, and let's plug it in. Our integral, which is now fully in terms of u, with no x in it, becomes, I'm going to remove the negative 1/4 out here, I'm going to say this becomes 1 minus u over 2 times square root of u, all with respect to u. This is the same as the last problem where we can just expand this u because it's a power, and then use our power rule. This equals negative 1/8 u to the 3 over 2 over 3 over 2 minus u to the 5 over 2 over 5 over 2. All of that is times negative 1/8 here. And our last step, we have to rearrange this in terms of x. So remember, u is equal to 1 minus 2x squared. So let's plug that in. Now this becomes negative 1/8 still, 2 times 1 minus 2x squared to the 3 over 2 power divided by 3 minus 2, 1 minus 2x squared to the 5 over 2 power divided by 5. And this plus c, don't forget plus c when you're doing indefinite integrals, is our final answer. So remember, sometimes when you're doing u sub, it's not going to be immediately something u du. Sometimes you might have to do more rearranging and you might have to plug this back in for x to make sure that your integral is fully in terms of u, because only then can you actually start applying your integration processes. Let's look at one last example. Let's suppose my problem is x over square root of 1 minus 4x squared dx. Now, this already looks like a problem that you could use a u sub for, because we have x to the 1 power here and x to the 2 power inside some more complicated function that we cannot immediately integrate. Let's say u is equal to 1 minus 4x squared. Therefore, du is equal to, 1 goes away, minus 8x dx. Let's rewrite the integral. So we have minus 8x dx over square root of 1 minus 4x squared. And to make sure my value doesn't change, I'm going to divide by minus 8 because I multiplied over here. This becomes du. This becomes u. Let's rewrite our integral. It becomes negative 1/8 times the integral of du over square root of u. This once again becomes pretty simple to integrate because this is simply our power rule. It's the integral of du times u to the negative 1/2. And when we integrate this using our power rule, it becomes u to the positive 1/2 over 1/2, so times 2. This is all times negative 1/8. That becomes a 1, that becomes a negative 4, so it becomes u to the 1/2 divided by negative 4. Let's replace u with x. It becomes, I'm going to move this up here, it becomes the square root of 1 minus 4x squared divided by negative 4. And that is how you do u substitution. The most important thing to note is that once you select your u, you have to make sure that the entire integral is in terms of u. So you cannot have any dx's lying around, and sometimes that will require further manipulation to the integral, like this multiplying and dividing by negative 8 here, to make sure that the value doesn't change.